In the Ohm's law experiment, you'll be doing a simulated experiment online, and the point is to study Ohm's law and how it relates to currents and voltages in circuits. Okay, so here's a simple circuit diagram with a voltage source like a battery or like the low voltage source that we use in the lab for some of the experiments. And this symbol over here is supposed to represent a resistor. It can either be a preset resistor like one of these, or it can be like it can represent a light bulb or maybe an electric motor or some sort of thing that resists the flow of electrical current. So when you see one of these circuit diagrams, the resistor symbol can represent different things. Usually it represents a regular old resistor, a preset resistor. And each of these resistors has associated resistance, R, and the unit of resistance is the ohm, which is 1 ohm is the same as 1 volt per amp. So it's the number of volts that you have to expose the resistor to in order to drive 1 amp. So for instance, if this resistor is a 50 ohm resistor, that means 50 volts per amp. You need 50 volts of potential across it in order if you want 1 amp of current to flow in it. And if you want 2 amps of current to flow, you'd need 100 volts of potential across it. So this is what Ohm's law tells you. So here's Ohm's law, V equal IR. It relates the voltage across a resistor to the current through it and its resistance. And you're going to be using this over and over in the lab exercise. So knowing the voltage of this voltage source and knowing the resistance of the resistor, you should be able to calculate the current through it. Now you're also going to measure the voltage across the resistor. So here's how you would wire up a voltmeter in order to measure the potential drop across this resistor. You wire it to the ends of the resistor because you're measuring the potential difference between the ends of the resistor. So in this case, you're measuring not only the voltage across the resistor, but also the voltage across the voltage source here. So now it looks like the circuit has just gotten more complicated because there's now a voltmeter in it. Do you have to worry about current going through here? Is that going to change the behavior of the circuit? The answer is no. A voltmeter resists, has basically an infinite resistance, so current won't flow through it. So it doesn't affect the behavior of the circuit. This is just depicting the voltmeter measuring the voltage. Now you're also going to measure current in this lab exercise, and in order to measure current through a component, you have to put it in series with the component because, see, in this case, the current will go through the resistor and then also through the ammeter. The current has to go through the ammeter in order for it to be measured. Again, the ammeter doesn't affect the circuit in any way. There's no potential drop across the ammeter because they resist electricity almost not at all. So here's how you're going to measure current and voltage with this system. And this should agree with your calculation using Ohm's law. Now here's a little bit more complicated system with 2 resistors in series with each other. So the current that comes from the voltage source will go through resistor 1 and then through resistor 2. So the same current will go through them. They should have the same current through them. And to measure voltage and current, you can hook the voltmeter to the 2 ends of this circuit. So here you're measuring the voltage across both resistors and the current through both of them. Now, the resistance of 2 resistors in series with each other is just the sum of the 2 resistances. So if you had the volt and ammeter set up like this, the current and voltage should relate to the total resistance, which would be the sum of the 2 resistances of the 2 things. You can also use Ohm's law individually for each of the resistors by itself. Here the voltmeter is set up to measure the voltage drop across just resistor 1, and Ohm's law will work for this. In other words, the current through resistor 1 times the resistance of resistor 1 will be the voltage drop across it. And likewise, here it's set up to measure just the voltage drop across resistor 2, and Ohm's law will work for that as well. And what you'll find out in this kind of a system is the voltage drop across the two resistors, V1 plus V2, will be the total voltage of the voltage source. So what about two resistors in parallel to each other? Here's a little bit different. Here's how you measure the voltage across there. They have the same voltage drop across them because their two ends are connected together. So they have the same voltage drop, but the currents are going to be different. Some of the current's going to go through resistor 1, and some of it's going to go through resistor 2. They'll have different currents that are running parallel to each other. These are said to be wired in parallel with each other. But you can use Ohm's law individually for each of these to calculate what the current is going to be in each case. And then you can measure the individual current. Here's how an ammeter would be set up to measure the current just through resistor 1. And here is how an ammeter would be set up to measure just the current through resistor 2. And you can use Ohm's law individually to calculate that current. Now here, if I put the ammeter here, this measures the total current through both resistors. And you can find the equivalent resistance of both these two resistors together, so you can do this kind of a problem by just calculating the total resistance this way. Take the inverse of resistor 1, the inverse of resistance 2, add them, and take the inverse of that. That gives you the effective resistance of the two resistors in parallel with each other, and that should satisfy Ohm's law for that case. And then the final thing you'll do will be to analyze this somewhat more complicated set of resistors. So our R2 and R3 are in parallel with each other, so you can calculate their effective resistance in parallel. And then those are in series with R1 and R4. So you can just add the effective resistance of R2 and R3 together with those to find the total resistance. And that's how you'll analyze this somewhat more complicated circuit.